Objective 4, Part 3. The first problem we're going to look at is a very simple physics problem where uh, ground level is h equals 0, and we'll have some initial height, what we'll call hi, and somebody's standing on this building. They're going to throw a baseball up in the air with an initial velocity vi, and it's going to be in, I said meters per second. It's going to be in feet per second. Just to give you some reference point, the fastest pitch is roughly 105 miles per hour, fastest major league pitch recorded, and that's about 72 feet per second. You can multiply miles per hour by 0.7 to get a rough estimate to feet per second, and roughly 1.5. You multiply feet per second times 1.5, that will give you miles per hour if you want some reference point. Given a situation like this, it turns out h of t is equal to negative 16t squared plus vit plus hi. This can tell you, given any time, this can tell you exactly where the ball is. This is an exact relationship. When we derive it, when we make certain assumptions, one assumption is that we're operating in a vacuum. There's no wind resistance. And for certain objects, if it's a heavy baseball at a relatively slow speed, it's probably a pretty good assumption. If it were a shot put, the wind wouldn't affect it. If this were a piece of styrofoam, well, guess what? This is a bad model. Wind would blow the styrofoam away. We also assume that this ball isn't going to deviate very far from its original position relative to the center of the Earth. And it's thousands of miles to the center of the Earth, and we're just doing this experiment over a few hundred feet. So we make those simplifying assumptions. You can derive this as an exact relationship. You can derive using basic mechanics. Now we have a situation here. VI is 48 feet per second. Somewhere 70, low 70s, 70 miles an hour, say. That's about as fast as an average high school baseball pitcher can throw about 70 miles an hour. So it's got some speed to it, but not blinding speed. And we're going to assume the ball is 65, or the building is 64 feet tall. Or you could assume the building's 60 feet tall and the pitcher's 4 feet tall. It's going to release it from 4 feet, whatever. But the initial height is 64 feet. And we're going to work a series of problems. This obviously gives you a parabola. It's parabolic. The trajectory is going to be straight up and straight down. But if you were to graph the height as a function of time, you'd get a parabola. It's a second degree equation. So first problem, find h of t. Well, it's fairly simple. We substitute negative 16t squared. That term's always there. This negative 16 is half of the acceleration due to gravity in feet per second. Half of 32. That's true near the surface of the Earth. The only way that would change is if you went to a different planet, or possibly the moon, where the planetary parameters change, the size and the mass. We need VIT. We said VI was 48 feet per second, so we have a 48t term. And then we add in the height, and that's 64. Now the next question is, when will the ball reach the maximum height? Obviously the ball is going to go up, stop instantaneously, and come back down. When's it going to reach the maximum height? Well, this is a parabola. This is A, this is B, this is C. And you can find t equals negative b over 2a. That's a formula you learned in 9th grade math. Negative 48 over 2 times negative 16, and that's equal to 48 over 32, which is 1.5 seconds. That's what it reduces to. Okay, now what is the maximum height? It's an interesting question. We can find h of 1.5. That's what this height equation is for. Given the time, we can find the height is negative 16 times 1.5 squared plus 48 times 1.5 plus 64. Okay, that's 2.25 times 16. And 2 times 16, 32, and 4, we get negative 36. Plus 1.5 times 48 is 72. Plus 64, this is feet. And we can add that up, and we end up getting 100 feet. You can verify that or do it on your calculator, but these two terms combine to be 36. 36 and 64 is 100 feet. So this starts 64 feet in the air with a given velocity, and after 1.5 seconds it stops, and it's actually gone a total of 100 feet. So it's traveled 36 feet above the starting point, and then it stops. So, okay. Here are a couple other questions. Make some space here. When will the ball return to h equals 64 feet? So I erased my picture, but we're standing in the building. It's going to go up and come back down. You can use a little bit of common sense here. In 3 seconds, 1.5 seconds to go up, and it's going to be 1.5 seconds to go down, 3 seconds. Well, in any event, it's a lot more fun to actually do the math. We can take 64, set it equal to negative 16 t squared plus 48t plus 64. And you can cancel these terms out, and we just have negative 16t squared plus 48t equals 0. And then you can factor negative 16t out, and we have t minus 3 equals 0. Okay, this factor gives us t equals 3 seconds, and this factor gives us t equals 0 seconds. Okay, and that's not surprising. It's not surprising at all, simply because this is where it started, and then that's 3 seconds into the experiment. So. And D, when will the ball, let me get a better marker here, hit the ground? Okay, it's going to go past the top of the building and then hit the ground. Well, we have h equals 0 feet. So I can substitute 0 into this equation right here, and we get 0 equals negative 16t squared plus 64t plus, or 48, sorry about that, plus 64. And then you could divide out negative 16 if you want to simplify this quadratic equation. My markers are a little bit old. And then negative 16 over negative 16 gives you t squared minus 4t, and 64 minus 3, sorry about that. And then that's minus 4 equals 0. And then you can factor that as t minus 4, t plus 1 equals 0. And that gives you t equals 4 seconds. This t equals negative 1. You can reject that. That basically says we could have, 1 second before it started, if we threw the ball at the ground and it went through this initial position with this velocity, it would have taken 1 second to get there given these conditions. So it takes altogether 4 seconds. It took 3 seconds to get back to original position, 1 more second to hit the ground. Okay, that's one problem. We have one more problem to clean up at the end, and that is where do these two functions intersect? F of x equals x squared minus 4x plus 2, and g of x equals x plus 8. We have a parabola and a straight line, and they might intersect. Several different things could happen. They could intersect at 2 points, they could intersect at 1 point, or if the line's down here, they could not intersect at all. And the algebra bears this out. If we just do the algebra, well, we can find a point of intersection by setting the two functions equal. When they intersect, the x and y coordinates are equal, and particularly the y coordinates are equal. We can make that assumption, and you assume that x squared minus 4x plus 2 is equal to x plus 8. Okay, and now we can solve for x. Minus x plus 8, minus x plus 8. And we have x squared minus 5x, minus 8, sorry about that. A little bit hasty there. Minus 6 equals 0. And that factors as x minus 6. X plus 1 equals 0. That gives us two x values. X equals 6 and x equals negative 1. Well, x equals 6, we have the x coordinates, we don't have the y coordinates. You can plug in either function. G of 6 is 6 plus 8 over 14, so we have the point 6, 14 to start. And also g of negative 1 is negative 1 plus 8 or 7, and so we have negative 1, 7. There are the 2 points. You could also, if you wanted to check, you could plug these two x coordinates into f. You should get the same result. So 6, for instance, 36 minus 24 is 12. 12 and 2 is 14. Since we started off with the assumption that they were equal, they should come out equal if indeed you did your work correctly. Okay, that concludes objective 4.